Hello class, today's lesson is going to be on force fields, and in particular we're going to focus on the electric field. To define a force field, we're going to just have a working definition, and that is that when a certain type of object is placed in a field, it will experience a force. That is, when the object is placed in the field, it's going to accelerate somewhere. Now we already know about the gravitational field. The symbol used for the gravitational field is little g, and when an object with mass is placed in a gravitational field, it starts to accelerate. So the type of object necessary is one that has mass. Okay. Now, so here we have a big mass that's going to create this gravitational field, and we can place in this gravitational field some small test masses. Okay, so these masses are really small, they don't really generate their own gravitational fields. We know that if we place this little test mass in the gravitational field of the big M, it's going to accelerate downwards, right? And we can likewise place it out here, and it will accelerate towards it. In fact, if we place it anywhere near the mass, it's going to accelerate towards this large mass M. Okay, so that's what the gravitational field looks like in the vicinity of this large mass. For the electric field, we're going to use a symbol capital E to denote the electric field. Now, anything with charge, like this big Q here, that has charge is going to exert an electric field in the vicinity of that charge. So if you place a small test charge, like this Q, out in that area, it's going to experience some force. Now the electrostatic force and the gravitational force are much different. The gravitational force can only be attractive, whereas the electrostatic force can be both attractive or repulsive. So placing this test charge in this area, we don't really know where the force is unless we know the sign of those two charges. So let's say for now that our big Q, the one generating the field, is a positive charge. Okay? The test charge is always going to be considered to be positive. So if we place the test charge in the area of this big Q, we know they're going to repel each other, and this small test charge is going to experience a force outward. If we were to place the test charge over here, it would experience a force out in that direction. If you place it close by, it would experience a force, and that force would be larger, but it would still be directed outward. So this is the directions of the electric field anywhere near our large charge Q. However, if our central charge were negative, then the only thing we'd have to do with these arrows would be to face them inward, and since the test charge is always going to be considered a positive charge. Okay, this one is always positive for that test charge. All right, so now the direction of these forces, the gravitational force, we know is always going to be an attractive force, which means that the direction of the field is always going to be toward the center of the big mass M1 that I've labeled in the diagram. Now what we said for the electrostatic force is that if the charge is positive, the central charge is positive, then the electric field is going to be directed away from that charge. If the central charge is negative, then the electric field is always going to be directed towards the charge. Now that we know the direction of the field, we can calculate the magnitude of the field. So we'll start with our definitions of force. So we know that for the gravitational force, Fg is equal to m times g. So it's the mass or the type of object times the field itself. So now we can solve for g, and g is just going to be equal to the force of gravity divided by the mass, and it'll have units of newtons per kilogram. Okay. Similarly, for the electrostatic force, we can define this as the charge, which is the test charge, this guy's the test charge, times the electric field. That is the definition of the electrostatic force in terms of the field. So then the electric field is really defined as the force per unit charge. It's how much force a 1 coulomb charge would feel. And the units are going to be in newtons per coulomb. So that is the definition of the electric field, and that's how we calculate the magnitude of that electric field. Now for a spherical mass, we could calculate the gravitational field anywhere around the vicinity of that mass. We know that the gravitational force is equal to g m1 m2 over r squared. And if I want the force on mass 2, the one that's out in space, then this is just going to be the mass of 2 times gravity, and this is equal to g m1 m2 over r squared. Now I can cancel out the masses, and what I end up with is an equation to calculate the gravitational field anywhere in space away from the central mass. That is the gravitational field. Now I'm going to do something very similar for the electrostatic field. We know that the electrostatic field is calculated by the electrostatic constant K times Q1 times Q2 over R squared. Now we had just defined that this electrostatic field can be calculated by Q times E. It's a force per unit charge times the charge itself, and that's going to be equal to K times Q1 times Q2 over R squared. Doing the same thing, I can cancel out the Q's, and that will leave me with an equation to calculate the electrostatic field anywhere in space around a point charge Q. So what this represents is the magnitude. This is the magnitude of the electrostatic field from a point charge. All right, so now how do we apply this? So let's say we have a scenario in which we have two charges, Q1 and Q2, that I've drawn here, okay? And they're equidistant from a central axis. Q1 has a charge of 4 times 10 to the minus 15. Q2 has a charge of 4 times 10 to the minus 15, but it's positive. And both of these charges are distance d away from this central axis. So both of them are distance d away. Now, if I want to calculate the electric field at a point that's on this axis but a distance x away, then I can use the equation that I have above here, the magnitude of the electrostatic field from a point charge. So first, let's label this length here as x. All right, so what I want to do is I want to know what the electric field is at this point on that axis. So first, I want to look at the direction of the electrostatic field. Due to just charge 1, I know that if I place a small positive test charge here, it's going to experience a force. Now, because charge 1 is negative, then the force on this charge is going to be attractive. So I know that I'm going to have a force that is directed like so, towards that charge. The force due to charge 2 on charge 1 is going to be slightly different. Charge 2 is a positive charge, and this test charge is going to be also positive because the test charges are always positive. So the force between charge 2 and this charge are going to be repulsive, which means that the direction of the force is going to be directed away. Now, because both charge 1 and charge 2 are equal in magnitude, and I have a lot of symmetry here in terms of the distances from the axis, then I know that the y components of these two vectors are going to add up, but the x component of these two vectors are going to have to cancel. So what I end up with is a resulting force that is going to be directed only in the y direction. Okay, so this is the direction of the electrostatic field at this point. Now we're going to use some geometry here. I can draw that line, and that is going to be the distance r from the charge in here, and I can define the sine of that angle as the opposite d over the hypotenuse r. And this is going to come in handy in a couple minutes. Alright, so now I want to calculate the magnitude of the electrostatic field. So what we said before was that the electrostatic field only has a y component, so that's the only part I care about. The electrostatic field is going to be a sum of the electrostatic field from charge 1 in the y direction plus the electrostatic field from charge 2 in the y direction. Now this is the magnitude of the electrostatic field is given by kq1 over r squared. And if I only want the y component, then I just want the sine of the angle. Okay. And to this I have to add kq2 over r squared. And again, I want the y component, or the sine of the angle. Now I can replace the sine of the angle with d over r, and this simplifies to kq1 d over r cubed plus kq2 d over r cubed. And in order to get the magnitude of the electric field, all I have to do is plug in the values. So I'll let you do that, and then in class I will check your answer. You can pause the video here until you're done calculating and then move on. For the last part of this class, I want to teach you the rules for drawing electric field lines. Okay? The first rule of drawing electric field lines is that the lines can bend, but they can never cross. The second rule states that the number of lines per area is proportional to the strength of the field. Okay, so now if we have a charge positive q, we know if we place a small test charge in the vicinity of this charge, then it's going to be repelled away. So you would draw a line that goes away. And then we draw an arrow for the direction of the force, or the field. So all around this positive charge, I would have these lines that would come out like so. Okay, so now, if I have a central charge of negative 2q, then I know that a small test charge is going to be attracted to it, so the field lines would go into the central charge of negative 2q. Now, since I've used 4 lines around our positive charge q, around this negative 2q, I should use more lines because the field should be stronger around the larger charge. Right? A test charge is going to feel more force around a larger charge than it would feel around a smaller charge. So, since the charge is twice as much, I should draw twice as many lines. Now, these two charges that I've drawn, this positive q and the negative 2q, these guys are very far away from each other, so their fields do not interact. However, if I place two charges close to each other, like these two, then their fields will definitely interact with each other. So, we know that around our positive q, you're going to have electric field lines that have to extend radially outward. And we also know that around the negative charge, they have to extend radially inward. The test charge is going to feel an attractive force to that negative charge q. If I were to extend these lines all the way out, then we would break that first rule, which is that the lines can never cross. So what happens instead is that the lines actually bend around and will connect. And you're left with a field diagram that's going to look like this. These lines out here will also be able to wrap all the way around. And that's what the electric field diagram would look like around those two charges. What this electric field states is that if you were to place a small charge here, right, and you placed a positive charge there, it's going to experience a force that's going to be directed away from the positive charge. It also experiences a force that's going to be towards the negative charge, and right at this point, it will feel a resulting force that is along that electric field line. That's what these electric fields represent, is that the net force on a positive charge is going to be directed like so, tangent to these lines. Now we'll do one more example where you have positive charges only. Okay. Around each of these charges, we know that there's going to be an electric field that extends radially outward. A small positive charge is going to be repelled by these two charges. Okay. But in the central area, there's going to be something interesting that happens here. Again, those lines cannot cross, so as they extend outward, they have to start bending away from each other. Now when we look at these two diagrams, we know that if you have two positive charges and you place them near each other, they're going to repel each other. And these lines, the bowing of those lines, shows that repulsive force. Okay? When you place a positive and a negative charge near each other, we know that those charges are going to attract each other. And these central lines in here show that force of attraction. All right, that's it for today's lesson. I'll see you guys in class tomorrow.